Hi and welcome to this ecology video on the rates of decomposition, which is for biology triple students only. So let's start by introducing decay, which is a breakdown of dead organisms, and it is caused by microorganisms such as bacteria and fungi, as well as detritus feeders or detritivores, which includes a whole cocktail of creatures that feed on dead matter. Examples could be worms, maggots, etc. And as decay of dead material is caused by living organisms, those living organisms require certain conditions to enable them to live and therefore decompose the dead stuff. So what on earth would they possibly need? Well, it's simple. What would we like? We want a decent temperature, and this links back to enzymes. More often than not, the enzymes that these decomposers have work in a similar way to the enzymes that we have, in that they'll work optimally in like the mid to high 30s. So they like warmer temperatures. However, if it's too warm, there is that problem of enzymes denaturing. And if it's too cold, the enzymes simply will not work. Another thing that they will need is oxygen. The majority of decomposers prefer to operate in aerobic conditions, and they would need that oxygen for aerobic respiration. And in doing so, they will then be releasing carbon dioxide and water back into the environment, linking into the water and carbon cycle that were covered in another video. There are exceptions, however. There are some microorganisms that can respire anaerobically, and I'll talk about those in a moment. How much water is available? Water is needed for many biological processes, so in moist conditions decay is faster. And also the number of decay organisms. The more of these you have, the faster the rate of decay. One of these factors constitutes one of the required practicals for the course, and that is to investigate the rate of temperature on the decomposition of milk. Now, this investigation can be done slightly differently in the case that you could look at some slices of bread and compare how they look on a daily basis if they are left in different temperatures. However, it's a very subjective way of looking at data, and it's qualitative data rather than quantitative data. So to improve the accuracy here, milk is used, and even though microorganisms are not used to look at the rate of decay, which remember means the breakdown of something, we are looking at the effect of the enzyme lipase on the breakdown of fats in milk. And as lipase is an enzyme and all decay operates using enzymes, we can draw parallels with how temperature is going to affect the rate of decay in decomposers. So to do this practical, you will need a test tube, and in that test tube you need to add some milk, 5 centimetre cubed of milk. To this add 5 drops of phenolphthalein, which is an indicator. Now you need to set up a pH of at least pH 10 into this mixture, and to do that you need to add 7 centimetre cubed of sodium carbonate, and this will set up a pH of at least 10, which when phenolphthalein indicator is exposed to pH is higher than pH 10, it turns pink. Now once this has been set up, it needs to be put into a water bath, which could be at any of these temperatures: 0 degrees C, 80 degrees C, 20 degrees C or 30 degrees C, or any suitable range of temperatures, and that would be the independent variable of this investigation. And once this mixture has calibrated to that temperature, so you may need to leave it for a minute or so, you would then add 1 centimetre cubed of lipase solution. So this is the enzyme now. So lipase, once added, will break down the lipids or the fats in milk, so this will be lipase here, into fatty acids and glycerol. And what we're really concerned about here is the production of these fatty acids, because as the solution becomes more and more acidic, the pH drops. And if it falls to below 8.2, the pink phenolphthalein will turn colourless. The faster that happens, the better the enzyme is working, the faster the rate of decomposition. So obviously, once a lipase has been added to the solution, a stopwatch is started, and there are 2 ways of measuring this, 2 versions of the dependent variable, and that could be to measure the time taken to go colourless, in which case you would have a graph that would have different temperatures along here and time taken to go colourless along the y-axis. Alternatively, you wouldn't necessarily need the phenolphthalein here, you would just need a pH probe that would be positioned inside this mixture at all times throughout the practical and will be hooked up to a data logger, which would basically plot a graph that looks like this. So over time, if we have these as minutes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So over a 10-minute period. As soon as you've mixed the lipase in, every minute thereon you record the pH of that solution, or the data logger will do it for you. And after you've done the test on one temperature, you would then need to do exactly the same setup at a different temperature. Now, to vary the temperature, you could, by using different ratios of hot water to cold water, make up these different temperatures, but you'd have to maintain that. A far easier way of changing these temperatures is to actually put this test tube with the ingredients, with the lipase, into water baths that are maintained electronically at those different temperatures. So after this practical has happened, you may get data that looks a bit like this when plotted on a graph. Here, this red line, the practical was done at 0 degrees C. There really wasn't a drop in temperature, and in fact the solution would have just stayed pink. And the reason for this is 0 degrees C is far too cold for the enzymes to work. Decay or breakdown of lipids in the milk did not actually happen. If we were to relate this to decay using microorganisms, decay simply would not happen, and in these conditions you're quite likely to get fossilized remains of those dead creatures if we were to allow them to not decay for millions and millions of years. The next line down, the green line, is for 80 degrees C. Again, there was a little bit of a drop in pH, but it just plateaued again. Decay didn't happen, the pH didn't drop really significantly at all, and the solution would have stayed pink in this case. And the reason for this is, even though I did mention that microorganisms like warm temperatures, 80 degrees C is far too warm, and in fact at that temperature the enzyme lipase, as well as any other enzyme that's needed to break down matter, would have denatured. So the actual shape of the enzyme and its active site would no longer fit the substrate. Then we have this blue line, which is for 20 degrees C. Decay does happen, and the pH does at some point drop to below pH 8.2, and as a result the pink solution would have gone colourless. And this is because the enzymes have got more energy to collide with and meet their substrate and break it down into different products, one of which changes the pH of the solution. However, at 30 degrees C, which is closer to the kind of optimum temperatures that most enzymes operate in, you can see that the breakdown was quite rapid, and actually within 1 minute enough of the lipid would have broken down into enough fatty acids to have reduced the pH of the solution to one that would allow the phenolphthalein to change colour or go colourless. So this is much more rapid. Again, drawing a parallel with this and decay using microbes, at warmer temperatures like 30 degrees C, the microorganisms have optimal conditions for their enzymes, their digestive enzymes, because effectively that's what they're doing. They are feeding off the dead matter and they're digesting it. So these digestive enzymes are working optimally. Decay happens much faster. So why bother studying this? The reason is quite simple. Decay is of importance to us, especially gardeners and farmers. Decay of dead organic material means that you can actually get some good nourishment and feed it back onto your soil. So this here is a typical compost bin, and compost, once it's ready, is full of nutrients that could be put back onto the soil to fertilise it. Done on a much larger scale, farmers might spread manure or something similar onto their field to make sure that by farming day in, day out, year on year, that they're not completely depleting all the nutrients from the soil that they make a living from. So in a compost bin, basically you have a lid that can come off, and inside the compost bin you can put anything that can decay. So any food scraps or grass cuttings, etc. As long as there is an opening for oxygen to get in, there is a way for bacteria and fungal spores to get in. You may want to add your own detritus feeders in there, like worms and maggots, or just simply wait for them to arrive, because they will. And as long as you've got oxygen for aerobic decay, it's worth making sure this doesn't dry out, so you can add water to it to keep it moist. The temperature, once it gets going, because all of these feeders in here, all the bacteria, all the fungi, all the detritus feeders, due to this aerobic activity, they will be producing heat. So actually the inside, if you were to take the temperature of the inside of the compost heap, it will be climbing quite steadily. In fact, you need to be careful that it doesn't climb too high, because then you'll get denaturing of enzymes. So the temperature is kind of self-regulating, although you may want to insulate a compost bin in the winter, for example. The other thing that's important to do with compost bins is to circulate it all. So giving it a stir occasionally would help mix all the ingredients together and get the oxygen from this top layer here fed into all of the matter that's in the bin here. Once ready, you actually get this soil-like sludge at the bottom that could be spread onto your garden to fertilise it and enrich it with nutrients. On the other hand, similar sort of food waste and fecal waste can be fed into something called a biogas generator. So in a biogas generator, you often have a container, like a drum, that could be buried underground, or it could be above ground. Waste material goes in, and again you have got decomposers, bacteria, etc. that will be feeding off and digesting this waste and releasing nutrients from it. However, when this is made airtight and all the oxygen from this big airspace has been used up, what you get in a biogas generator is anaerobic decay. And when that happens, a product gets made, which is methane gas, which can be burned as a fuel. So this methane gas actually gets collected from this outlet here, and then when the food and fecal waste has decomposed to a point where it cannot decompose anymore, it becomes very useful as a fertiliser. The main issue with a biogas generator is making sure it maintains a constant temperature to keep the microorganisms respiring, and the biogas cannot be stored, it has to be used instantly. Thanks very much for watching, and do check in again soon.